There we go. Okay, so what number, Bill?
39.
39. Do people second that? Do
Yes,
people second
I
this?
second that. I anti.
No, I do not want you to do that first. You've never done one like this before, so what might be a good thing for you to do? You know what you're doing. You know what you're trying to find, but what should you do first?
Simplify.
Nope. Graph it. Thank you. How many people actually drew a picture of what this looks like? None of you did? Therein lies a big part of the problem. Since you've never actually integrated an absolute value function before, it's probably a good idea to actually integrate this, okay? Actually graph it. So we're going to graph this. Equal to the integral from -1 to 0 of something dx plus the integral from 0 to 2 of something dx. What goes right there? That's the big question. That's the function itself. It's this function right here. What is that function? What is that function?
3/2 x.
Nope. 3x. Goes from -1 to 0 of 3x dx plus the integral from 0 to 2 of what? Down 2 over 2 is?
-1. -x.
Negative x dx. The question is, where did those come from? How can you get those functions without actually making this graph? Where do those two functions come from? Where does 3x come from? Where does -x come from? We're going to look at the function f of x is equal to x minus 2 absolute value of x. All absolute value functions, well, simple absolute value functions like this can be broken up into two functions. F of x is equal to, when is f of x equal to just x minus 2x? When what? And when is x equal to x plus 2x? What does the absolute value function do to the x value?
It breaks it into two.
No. When you take the absolute value is effectively not there when x is positive. Do you agree? But when x is less than 0, what do you have to do to the overall absolute value? Make it negative. So you make it x plus 2x when x is what? We just less than 0, exactly. So what are our integrals going to be? So, oh wait, what is x minus 2x? What does this simplify to? Negative x when x is
Greater than
0, and it's equal to 3x when x is less than 0. Is that exactly what Maddie graphed?
Yeah.
That is exactly what Maddie graphed. Okay, so let's go back up here. So what do we oh, look, we're evaluating this. This is 3 times the integral from -1 to 0 of x dx, and this is minus the integral from 0 to 2 of x dx. Exactly. So let's take this. I'll just skip down for a second. Right here. What's the integral of x? 1/2 x squared. So this is 3 times 1/2 x squared evaluated from -1 to 0 minus, what is it? Same thing, 1/2 x squared from 0 to 2. Oh, the dx is gone. Yep, correct. So this is going to be 3 times 0 minus 1/2 times -1 squared, like that, minus 1/2 times 2 squared minus 0. So what's that? 3 times what? 3 times what?
-1/2.
-1/2, yep. Minus what? 2. So what's that come out to be? Oh, it's -3/2 minus 2, which is what? Is that exactly what we got up here?
Yeah.
Yay, it's the exact same thing. Yes. So when you see that you're integrating an absolute value function, you need to break it into two functions. And what are you looking for? Where the function... It's not necessarily equal to 0, it's where the point is.
The x-intercept.
No, it's not necessarily the x-intercept.
The vertex.
The vertex. You can call it the vertex. That's a better way to say it. You're looking for the vertex. Exactly right. So, I mean, I could ask you this. Like, what's the integral from -3 to 3 of x minus 3 times the absolute value of x plus 2 dx? I could ask you that. What are you going to need to find first? The two functions, that's correct. But what do you need to find first? We just said it out loud.
Where the vertex?
The vertex. We just said it. The vertex. What's the vertex of that absolute value function? Find it for me. What is the vertex? So on this one, since the vertex is 0, 2, set up the integral for this one right here. Don't evaluate it, just set it up. Okay, so now when we do this, what does it become?
4/5 x to the 5/4.
4/5 x to the 5/4 from 0 to 1, so that's 1 minus 4/5, which is?
1/5.
So did we get the same thing?
Yeah.
Overall, though, in terms of paths, which one was easier? Well, this is conceptually a little harder right now because it's the first time we've integrated with respect to y. But overall, looking at the math we have to do, which one would you rather do? I'd rather do the y in this case. There are certain cases where it's not going to be so closely related in terms of difficulty. In some cases, you're going to look at them and be, oh, it is much easier to integrate with respect to x here, or it's much easier to integrate with respect to y right here. Do you understand that that's going to be the case? Just believe that and watch out for it. So here's another tool you have. Do you have to integrate with respect to x? No, you can integrate with respect to y. So basically, instead of scanning from left to right, you're scanning from
Right to left.
no, bottom to top. Bottom to top. And just that's actually really important. If you reverse the order of integration, you're going to get the flip of the answer. So remember, you're either integrating from left to right or bottom to top. Remember that. Yeah, so you have the integral of sine x over cosine x dx squared. Yep, that's correct. So that's 1 over cosine x times what? Tangent x, right? dx. What is 1 over cosine? So this is secant x tan x. The derivative of what is secant x tan x? What is it?
Secant x.
Secant x, exactly. Plus c. Done.
Done.
Success on that problem completely relates on your ability to recognize basic trig derivatives. Going back up
My
here,
problem.
what do you have to do on this one? Yeah, you need to remember that sine 2x is equal to what? 2 sine x cosine x. You have to remember that.
I would assume
Forgot that.
Yeah. Or here's the thing. At minimum, you need to recognize that sine 2x equals something else and go look it up. In this case, does it simplify really nicely? So you have 2 sine x cosine x over sine x dx. What cancels?
Sine x.
Sine x, you get 2 times the integral of cosine x dx. The derivative of what is cosine x?
Sine.
So it's 2 sine x plus c. Done. Personally, so then you might think to yourself, okay, what is the integral? What power is the integral going to be to? What power are you going to raise it to? To the 3/2. So it goes from 1/2. You add 1, it's going to go to the what?
3/2.
3/2. So the integral probably is going to be something like 2x plus 1 to the what? 3/2. Let's say that's the answer. If we wanted to say that that was the answer, how would we go about checking it?
We would derive it.
We would take the derivative of that, right? So if we take the derivative of that, what would it be? If we did d dx of 2x plus 1 to the 3/2, what would that be equal to? What do you bring to the front?
Shouldn't it be 2/3?
Ah, so you want to put a 2/3 out here.
Yep.
I think that's a great thing to do. Okay, you're seeing some of the problems, so we do this. We put 2/3 d dx. Okay, great. So what's that going to be equal to? Well, it's going to be 3/2 times 2/3, 2x plus 1 to the what? 1/2. But then what do you have to multiply by here? By 2. We took care of this. We now have 2 times 2x plus 1 to the...
We had that exact problem.
Oh, great, there's a 2 there. Okay, how could we take care of that too?
You multiply it by 1/2.
1/2 to begin with. So instead of 2/3 right here, what should we put out there? We have 2/3 and 1/2. Don't simplify yet. 2x plus 1 to the 3/2. If we take the derivative of this, the 2/3 and the 3/2 cancel, and the 1/2 cancels with the 2. So d dx of this will equal what?
The answer.
The answer we want. It'll equal 2x plus 1 to the...
1/2.
So how would you, if you had to give a name for this method, what would you call this method right here?
Guess and check.
Yeah, guess and check. You maybe use logic, right? You do it. Oh, it doesn't work. Can we correct for it? Sometimes that's going to be good. Sometimes you're going to look, oh, I know what that is. That's not bad. What's the problem here?
There's a fraction.
It's a fraction. You get an x. There's an
It's a
extra
big
x
chain
out there.
rule.
The chain rule comes into play. it gets more complicated. So here's the thing. Certain easier use substitutions are just easy ways to keep track of things that you might actually be able to do in your head. But there are certain circumstances where you're really not going to be able to do the logic in your head. We basically took care of problems here. We took care of that 3/2 by putting a 2/3 out front. Then we noticed we're kicking out a 2, so what did we put out front?
A 1/2.
A 1/2. So we took care of the problems individually. Are you always able to keep track of them in that nice of an order?
No.
No, you're not. So let's take a look at this first one here. If I said u is equal to this, let's do it this way. If u is equal to 2x plus 1, can someone tell me what du is equal to if I take a derivative of both sides? Du is equal to what? If I take the derivative of both sides. 2 times dx. Are we okay with that? If I take the derivative of this, if I take, what is the rate of change of both sides? Are we okay with that? Okay, what does dx equal? Du over 2. I'm going to take this right here and look at this again. So what does that mean we now have? We have the integral of the square root of what? U. But instead of dx, what am I going to write? Du over what? 2. What can I bring out to the front of that integral? What? 1/2. So I have 1/2 the integral of the square root of u du. What is the square root of u? U to the what? 1/2 du. What's the integral of the square root of u, or u to the 1/2? What's the integral of u to the 1/2? 2/3 u to the 3/2. But what does u equal? What does u equal? What was our original substitution? 2x plus 1. So what do we do with this? Substitute back in, and what do we have? 1/2 times 2/3 times 2x plus 1 to the what? 3/2. Is that exactly what we got before? That's exactly what we got before. Don't obsess over the details right now. Let's just do another one and see how this helps.
Don't you have to still do...
Can you simplify the fraction?
Well,
yes, you can. But for
you
yeah, go ahead.
You have to still multiply it by du.
Nope. When you integrate, the du goes away. Let's take a look at this one. This is even more important because it's going to get more complicated. Okay. Just look at this. I don't understand what's going on. So let's look at this one. Hi, Jackie. You can ask questions? Okay, so u is equal to that. Can someone tell me what du is equal to? Negative 8x dx. What does dx therefore equal? Over negative 8x. So now what do we do? Substitute. So what does this integral become? X over what? The square root of u. Good. Times what? Over. What is the glorious thing that now happens? That is exactly what you hope. The x's cancel. What can you bring out to the front? 1/8 times the integral of u to the what power? Negative 1/2 du. Can you integrate u to the negative 1/2 pretty easily?
Yeah.
Yeah, it's going to be negative 1/8 times the integral of what? Tell me.
Negative 1.
U to the what power?
Negative 3 over...
Nope.
1
U to the 1/2, and what do you bring to the? What do you put to the front? 2. The du goes away because we just integrated. So what does this become? Becomes negative 1/4 u to the 1/2. But what does u equal? What does u equal? That. So we end up with negative 1/4 of what? 1 minus 4x squared to the what power? To the 1/2. How would we check this answer? Take the derivative. So let's actually check this. So here's our answer. If we want to check it, we do d dx of what? Negative 1/4 times 1 minus 4x squared to the... Let's see what happens. What do we bring to the front? It's going to be equal to negative 1/4 times what? 1/2 times 1 minus 4x squared to the what power?
Negative 1.
Times what? Negative 8x. What cancels here?
The 8 and the 1 over 8.
The 8 and that cancels, right? And the negatives turn positive, right?
Yeah.
So what are you left with? You're left with just the x You're left with x times 1 minus 4x squared to the,
Negative 1.
which is x over 1 plus, or sorry, it's 1 minus 4x squared to the 1/2. Is that exactly what we wanted?
Yeah.
It is. So here's the question I have for you. So this method right here, it works. If I just gave you this question, what's the mysterious thing? What's the Yes. This right here, finding / guessing this, is the key. Are you always going to choose the initial right u-substitution?
No.
No, you are not. You're not initially going to always choose it. You're just going to have to test it. If it doesn't work, you're going to try something else. Times what?
dx.
5 times the rate of change of dx. So what does dx equal?
Du over 5.
When you substitute, you therefore get e to the times what? Du over 5. So you get 1/5 the integral of e to the u du. What's that equal to? What's the integral of e? Yeah, so it's going to be 1/5 e to the u. But what does u equal? So this is equal to 1/5 e to the 5x. Essentially what u substitution is doing is helping you take care of those fractions or extra bits that pop out. It helps you cancel them. It helps you get rid of them. When you integrate, let's say I gave you something like this. Here is a stage at which you know something is wrong. Let's say you did your u substitution and you ended up with this. What's the problem? What's the obvious problem? Nope. There's still an x. Or you could, it's still an x because du is dictating which integration you're doing. If you get to a point where there are x's and u's and they don't cancel, or you just chose a u substitution that doesn't work. If you do this, when we look right here, the magical step that's going to make you feel really good right here, what was the magical thing that made you feel real good right here? This right here. That's a happy step because you cancel the x's and you're just left with u's. This is single variable calculus. You're doing single variable integration. They need to get out of there. So if you're ever cruising along and you're like, oh, I'm going to do the integral of x over the square root of u, you should be like, no, don't try to do anything. Because in this case, they're both variables, but you have only one differential right here. Okay? One other thing I want to clip, and the bell's going to ring